Bonjour, my name is Elie Bursten, and today, with the help of Jean-Michel and Rémi, we're going to tell you about how we went about attacking encrypted USB keys. So recently, we ran a survey and asked people who have a USB key where they store corporate data, did you ever lost one of them, or is one of them was stolen? And we had 13% of the survey respondents said, yes, I lost one of those. So that means that one way or another, someone will get the hand of your data through an encrypted USB key. So that begs the question, if I'm using an encrypted key, is my data safe? Can I sleep at night? Or do I have a leak on my hand? Well, to answer this question, we need to know, are these encrypted USB keys truly secure? And the best way to do that, hey, we are at the security conference, is to audit them ourselves. Because we couldn't find online any good methodology or correct evaluation of the security of those. So today, in the real spirit of Black Hat, we're going to show you real attack against real keys that we found during our audit, and we want to share with you the journey where we did audit the key for our own purposes because we feel it's useful for the community as a whole. We also would like your help into making some of the attack working, because some of them who are going very, very deep into the hardware require a lot of work and a lot of understanding that we don't necessarily have, and we would love to get more people who know this stuff to help us out so we can all have a very nice methodology. So we'll show you the attack we have, we'll show you where we are, and hopefully at the end you will be inspired to work with us, and all of us can have a better, stronger methodology for those encrypted keys that we give to all our users to protect our corporate data. Sounds good? Yes? Thank you. Okay, so to be clear, we have the key here. After the talk come, and you can show you how many of them we broke. We broke the selection of those. We'll show you a few demos as well. We have even live attacks, hopefully at the end. So let's get started by quickly recapping. You should sit, guys. Sorry. Okay, we're going to start with talking to you about how a encrypted USB key looks like from inside. Okay, so this is the diagram of it. So you have obviously the USB plug and the PCB where your electronic components are. Then you have something which we call the controller, which is usually a microprocessor, which is also in charge of doing the cryptographic operation and ensuring that your key stays secure. And of course you have the storage where you store all your data. What the extra price tag comes from those keys is obviously the controller, which contains the crypto and stuff off, right? And then you have some sort of input mechanism who the controller takes input from to know that you have the right password. Might be a fingerprint, might be a PIN code, might be a software, might be a RFID tag. Either way, the controller is the one who is the gatekeeper of your data. So here's the real one. Same thing, right? You have the controller in the middle, and then you have the storage on the right side. Exactly what I described to you. We also see some keys which are more compact, and where they actually baked the controller and the storage into the same silicon, sorry. So it's harder for us to analyze because we can't obviously get out the chips out of the hardware key. The thing on the right side is the fingerprint reader where you can put your thumb and then unlock the key. All right. So the first question to answer is, why the hell are we doing a audit methodology for security key? We have the NIST, right? And the NIST have certification for USB key. So why redoing something which already exists and is working? Well, let me tell you about the NIST methodology so you can see it for yourself. There is two certifications. The first one is the FIPS 140, which is supposed to verify how cryptographic operations are done. It's a disclosure process by every vendor which is certified, and it's going to be validated by the NIST. There's another one, which is the FIPS 197, but basically to say I'm using AES, so we're not going to talk about this one. So FIPS 140. Well, to explain why we want something better, or actually more comprehensive to be clear, is because they're only interested into the cryptographic operation that the key is doing. Everything from manufacturing to security of the PIN input or everything like that is not covered by certification, so there is a lot of room, as we will see, for attacks which are not covered by the certifications. That's why we would like and advocating for a certification which is more comprehensive. We have another way to explain that. Before that. And we also found, we did review those documents very thoroughly. We spent tons of time looking through every certification and looking at this. Here's an example of the certification for the Iron Key. And what is a little bit concerning for us is, as you can see, it's for the Iron Key, except the documents say, well, it's for the Data Traveler D4000. So somehow, some way, the NIST validation process failed here, and they actually have a document which have a lot of copy-paste, and so we're not even sure the document is correct. And again, this is very hard to verify because it's baked into the silicon, so we would like to have a little bit more thorough verification when the document is submitted. Another way for us to summarize what the NIST is for us when we looked at it is this. Basically, if you trust your security to the NIST, you are missing a lot of things, so we would like to cover them today. So we come up with a new methodology, and we're going to walk through to the basic, and then we'll go through a few attacks to illustrate our point. So what was the first thing we did is we separated the attackers into 3 categories. So the first one we call the serendipitous attacker is the opportunistic attacker which has minimal resources. That's someone who will find a key on the ground or someone who will grab a key from a desk and have no prior knowledge or is not very resourceful and will try to plug it and try to do something. Probably the most common type of attacker. The second type of attacker are professional, either for hire or for business company who will try to go and have in-depth knowledge of how encrypted key works, and if there is an attack, they will know how to carry it. Last but not least, we have what we call state-sponsored attacker, which is just a fancy word to say someone who really is after a specific data, which might be on the encrypted key, whether it's like a specific set of cryptographic key or a specific document or backup data, and they will make a large investment to break a single key. And the difference between a professional and a state sponsor is a state sponsor is more interested into breaking one specific key, whereas a professional would be more interested in breaking as many keys as possible, right? So 2 different mindsets. We also have 3 types of impact. The first one is weakening the security, which is basically, it's not a flaw by itself, but it actually makes our job easier as an attacker. The second one is a single drive break. So basically the attack allows you to break one key and recover some of the data which is in one specific key. And the last one is what we call a full break, which is like there is a logical flow inside the key, and you can recover the data from every key which have the same model and the same making. So what do we want to cover during the audit? There is 5 categories that we would like to cover because we believe those 5 encompass most of the attack you can carry out. Those 5 are manufacturing, secure manufacturing, how you manufacture your key such that it's actually more resilient to attack. Second is input security. How do you make sure that the input part of the key is actually safe? Third is the controller security, because obviously you don't want the controller to spill your secret and properly destroy the key. Third is as an is a cryptographic operation, make sure that you use correct crypto. And last but not least, you want to verify storage, where you would want to make sure that the data is really encrypted on the storage device, on the chips itself. All right, so we're going now to go through each of those 5 in turn and show you a bunch of attacks. And Jean-Michel will start with talking about defensive manufacturing.
Thanks, Eddie. So for the manufacturing, the goals we had in mind during the investigation and the audit was that it's the first layer of protection you will get, because it will mitigate hardware attacks. It will slow down the analysis by hiding the components and preventing people from tampering with the key. But it's also the last layer of protection, because that's also what will protect your key against very advanced attacks such as electromagnetic radiation measurements with Tempest-like attacks. During the audit, we discovered some keys which were providing some copper shielding, and this copper foil was actually connected to the ground of the USB stick, making the protection effective. Some other keys were also using some epoxy, like this one, which basically prevents you from reading what components they are using, and it's quite tedious to remove that layer of epoxy. We also saw some other keys during the audit, like this one, and the coating didn't look like real epoxy, so I started using a piece of rag with some acetone, rubbing into it, and the piece of rag was turning into black, so it seems to be efficient. So I was keeping the key into a bath of acetone over the night, and I ended up having a very clean USB stick at the end. So be careful to use real epoxy. And on this one, this key was actually certified by the NIST, and on the documentation they were actually stated that it was coated in epoxy, which means that the NIST validation process was failing at seeing it was not real epoxy or validating that it was real epoxy. Another layer of protection is laser etching the references of the component. Even if it means security through obscurity, it's really hard to find the datasheets of the USB controllers that are used there, except when they leak. So if you don't have the reference, it will be very hard to identify which component they are actually using. It's hard to see on the picture, but it's not just a black marker, it's really milled. So the reference is not there anymore. But that's an extra cost at the manufacturing pipeline. So you have to be sure that you use the right service, because here they pay the extra for nothing, because we can still see the references of the component. Another thing that you have to pay attention at manufacturing is about the debug ports that are used to test the USB key at the manufacturing level or during the development process. And on this one, on the far right side, you can see some pins, some small solder pads that are there and labeled, which are actually used as a debug port, and you will see later on an attack leveraging those. And so this is how we summarize for each category the different control points that we have. They are ordered by the level required for the attacker, and then also by the impact that it means. And now I will let Remy talk to you about the input mechanism.
Thanks, Jean-Michel. My name is Remy. I'm a software engineer at Google, and I'll tell you about the security of the input mechanism of the keys. We identified two main components. The first one is that only valid users are able to unlock the key and have access to the data. And the second one is that we should not be able to add new user to the key. During the audit, we had multiple kinds of input mechanism on the key we selected. The first one is the pin pad. You enter a number and then you unlock the key, you get access to the data. The second is using a badge. You swipe the badge and it unlocks this hard drive. Then we have the fingerprint reader. Same thing. You put your finger on the fingerprint sensor and it unlocks the drive. And last is the software based. So you plug the key and you have a first partition that pops up that gives you a software in which you can enter a password. And when you type enter, it will unlock the key if you gave the right password. Let me tell you about the first attack we found during the audit. It targets a fingerprint-based key on which we can replay an nlog command. The impact of this attack is a full break, meaning we can actually recover the data of all the key of this model. And we rate this attack as doable by the professional as you require a few tools. This kind of attack is not new, and actually in 2010 another model of key was found vulnerable, where you could recover the data without knowing the password. Here is the new model. It's a fingerprint based, you swap the finger, you unlock the key. When you open the shell, you get this PCB. On the left you have the USB controller. Then on the right, you've got the fingerprint sensor. And on the far right, you see pseudo screen and pins with the label of a debug port. So you've got a USB, you've got clock, and you also got RxD and TXD, which are a serial line. So we mapped the PCB, and here is the logic diagram of the key. So the sensor is connected to a fingerprint manager. The fingerprint manager reads your fingerprint. This fingerprint manager is controlled by the USB controller over the serial line. And this is the USB controller that's responsible for unlocking the storage and decrypting it. You can see we found a design flow in the serial line because it was not protected and we were able to read what was sent over the serial line. Here is a picture of the attack. We started by plugging the key on our computer, soldering some wire on the debug pins, and then wired that to a serial port, here a bus pirate. And we conducted the attack by simply using the key normally, and using the bus pirate, we read what was going on the serial line when we swiped our enrolled finger. And what we saw was a static command saying which was the number we swiped. Just a number, like finger number 0. Then we unplug the key, plug it back again, and using the bus pirate to write the exact same command we saw the first time, and it would unlock the key. Let me show you a small video of the attack. So on the laptop on the left, you see the actual command that you have to send over UART. Plugging the key, blue light, wiring the bus pirate. On the right, you got the Windows laptop. I send the command, and you see the partition got opened on the Windows with access to all the data without using the fingerprint. During the audit, we found another attack, which was that the input tag of the USB hard drive could be cloned. And the impact of this attack is only a single drive, because you clone the tag of the drive you want to attack. And as it also requires some tools, we rate the attacker as professional. Here is the vulnerable model, along with the tag that you have to swipe to unlock the drive. When you open the drive, you have this PCB with the SATA port that's used to connect to the actual hard drive that will be encrypted. The RFID code used to read the tag with its little controller, and the configuration. And to conduct the attack, you need an RFID research tool. Here it's a Proxmark, and a reprogrammable RFID tag. It will be used to clone the tag. Here's a video of the attack. Here is the open USB drive. Red light means it's locked, and we will use the real tag. Green light, it's unlocked. Using the RFID research tool, we read the content of the tag and write the content back into the reprogrammable tag. As you can see, it's pretty fast. And then using our custom tag, we swipe it just like the real one, and you see green light. The drive is unlocked. We've got access to all the data. Summing up for the input audit criteria, we found the one in bold are the one we actually found attacks against, and which models are vulnerable, which are the unlock command that can be replayed, and we found an attack where the input could be cloned. Summing up with the impact and the kind of attacker that can conduct the attack. Moving on, I'll let Ellie talk to you about the security of the controller in USB keys.
Thank you, Remy. So the third part we want to cover, as Remy said, is a controller, which is kind of the brain of the key. And here we have many goals, because that's the place where most of the security happen. The first one is, and that seems obvious, but you'll see we have some attack against it, is the controller is supposed to protect your secret, which means the controller should never leak your password or the AES key. That seems obvious, but somehow some people fail at it. The second thing is you expect the controller to lock the drive when it's needed, meaning if you unplug the drive, well, the drive should be locked, and if you have a glitch on the USB port, it should lock itself, and so forth and so forth. So we expect it to do that. We also expect the drive to destroy secrets, at least zero out the AES key so that the drive becomes unusable when it's under attack after a few unsuccessful attempts. You would imagine, again, that is something that is granted. Turns out it's not. And last but not least, and this is more like wishful thinking, we would like to have firmware attestation, meaning today there is no guarantee that there is not a way to have a backdoor firmware. We have no way to attest that the firmware run into those keys is really the one we can audit, because we have no way to have firmware attestation. So we would like in the future to have keys who are fully attested. Very, very similar to the secure enclave that we start to deploy into Intel, right? We would like to have the same thing for the key, because we can't trust that the key is really operating the firmware we have. So hopefully that's going to be in the next generations. So the way we do some of the analysis, and that's a little bit of a behind-the-scenes stuff, is we do a lot of interceptions. We'll talk about how we do interception between the memory and the controller later on. Jean-Michel will tell you about that, but we also do interception between the key and the computer, and we monitor what happened. The reason why we do it at the hardware level is because we really want to make sure we see everything happening on the USB bus to make sure we don't miss anything. It seems a little bit overkill, but turns out we found a very cool attack that I'm going to demonstrate to you in a second by doing this kind of interception. And maybe this, to show you what happened in practice, this is what it looked like. So we have in this blue box is actually a dedicated hardware which allows you to do interception of USB traffic full speed even for USB 3, which is very difficult due to the timing and the speed. And it basically has 3 ports. One, you connect your key, so that's one of the keys we connected to it. And then the second cable in the front goes to the target laptop or target desktop. We use a laptop because it's easier to put on the desk next to our desktop stations. And then the cable at the back go to our desktop station where we do the recording and we do the analysis and we use custom software for that. So that's what our interception platform looked like. And we've been running it on every key we have audited to make sure that we understand exactly how the communication between the computer and the key are happening and making sure everything is square and fair. Turned out it's not. And it gave me what is my favorite attack of the talk, because I think this is the most mind-boggling one. This is also the one we do feature and we share it on social media because we really feel it showcases how dangerous this thing can be. It's against a fingerprint key. This is one of those, and we were actually wondering how many of those were having this problem, so we bought a few other brands which we were believing having the same chipset, and it turns out they're all vulnerable. So we have this one, and we have a bunch of others we have here. Actually, if you would like to see the demo live after the talk, please come on here or on the wrap room and we'll show you live the attack, show you how easy it is. So it's attacking fingerprint keys. We deem it a full break, and even a surreptitious attacker knows how to do it when you know what to look for. And this is as insane as you can recover the master password. So do you want to see it in live? Yes? Okay. So the key, unplugged it, that looked like this. Nothing to see except the fingerprint reader. Nothing to see, right? So you have the fingerprint reader and the controller. So here's how it goes. We made this one very nice because that's our demo trailer. So you have someone on a coffee shop and which is leaving, and the attacker is spotting a key, so he's going to steal the key, right? And the key has a fingerprint reader on it. And so later, when he's back to his lair, he's going to try to log for the key, and obviously you can't, right? Because the fingerprint reader do work as intended, so you can't. And then you're really sad. But turns out there is a secret USB command which allows you to recover the master password. And that's how fast it is. So all you have to do really is you say, oh, I'm an admin, here's my master password, please do unroll my fingerprint. And then you add a new user, let's call it, well, I don't know, AVL user. And then you click on next, and you start to tapping your finger. And a moment later, you will have your fingerprint unroll as a legitimate user into the key. That's how bad it is. So any of those keys are definitively broken because you can extract the password from the controller. Yeah, I still have people shaking their head. Yep, that sucks. I can't imagine how someone designs security product would do that, but actually they do, which is why we need to audit all of them and make sure we verify clearly the spec. Even if you think it's obvious, actually it turns out some people still make mistakes, and we're here to protect our users. So another one. You would assume a controller will lock after like 5 or 6 attempts. That seems obvious, right? You should not keep going it. It turned out that when we did our audit of a encrypted hard drive, who use a RFID badge, we found out that's not the case. So we deem it again a full break, and a surreptitious attacker can do it because that is again very easy to do. So here's a badge, so you can use them or use like a Proxmark to start to do the brute force. It turns out they do log the hard drive after 6 attempts. The only problem is when you power off and on, counter goes back to 0. So, with a simple electronic manipulation, we turn on the voltage, we turn on the disk, brute force, turn off, You can brute force it as much as you want, and so basically it's completely useless. Anyway, so audit criteria to sum up. Well, the device should burn after n successful attempt, and you should not be able to reset the counter. Obvious, but well, important. And the password and AES key should not be able requested from the thing. We also have other bunch of stuff like the AES key needs to be regenerated and so forth, and those are more technical things. They will be in the slide, and later on we'll publish the full methodology on GitHub so you can actually download it and help us to make it even better. So moving on to the fourth part, which is cryptography, we don't have much to say because, of course, we know what we want. We want data to be properly encrypted. And we want the encryption key to be truly random, which means you should not use the same key over many, many devices. And you want the key to be truly random, meaning we can't guess what the key is for a given device. We did see that, for example, in Wi-Fi routers a while back, where they were deriving the key from the MAC address. Hopefully no one does that for USB key. The problem is the cryptography is literally baked into the silicon, which makes the audit very, very difficult and almost impossible if you don't have the correct spec. So we feel that the tests are too expensive for us to do, so we kind of skip all of them, and we hope to solve that not by going ourselves doing the hardware audit, but instead having a better certification process and having manufacturers disclose more information. So that being said, we did find a few oddities. I'm going to just mention a few of those. People use outdated crypto in certain keys. We found one key who used RSA 512. Don't do that because you are vulnerable to factoring attack. And we also found some key who are doing file-by-file encryption who are using RC4. Of course, RC4 is considered a broken cipher, so they should use, I don't know, AES, and they don't. Or they can use any stream cipher like Cha-Cha 2020 or something like that, but they still use very outdated crypto. So we come across a few things where even by just doing the audit, normal audit, we found some oddities, but for the very hardcore and in-depth analysis of the crypto, we believe it should be done at the certification level. So here's a bunch of recap of what we think should happen. Our encryption key should be unique. There is no recovery master key, so no backdoor, and data is encrypted using AES and Eurostandard. That would be the three main things. And then we have a bunch of technical requirements that we think are useful to improve the security of the key. All right, for the last part, and which is the most experimental part of the talk, and you will have no video there, would be how we attack storage. So Jean-Michel will walk you through that.
Thanks. So the goal we had in mind for the storage audit was obviously what you expect from the encrypted USB key, which means doing a full disk encryption. But also providing you with some integrity check so that if someone tries to tamper with the data, it will be detected and prevented. Extracting the content of the storage chip appears to be not easy at all. First, you have to do the chip removal, which means potentially go through the layer of epoxy until you get access to the component, then remove the component from the PCB. Then you have to dump the content of the memory. Because of the way the memory technology, the flash technology works, you also have some algorithm to compensate for the read errors that you will have, and you have to understand that algorithm to emulate it and recover the real data. Then you have to undo exhaust scrambling algorithm that is mainly used by people, by manufacturer. This is not a security feature, it's just to optimize the lifespan of the flash memory. Same thing for the next step, you have to interleave blocks the right way, it's just for the lifespan of the chip. Then you have to undo the file translation layer. If you're familiar with the x86 architecture, it's like the mapping between the physical memory pages and the virtual memory pages. So you have some area storing some metadata on the flash, and it will explain to you or to reorder the memory pages in the right order to get the file system back. Once this is done, you have to strip away the metadata you just used. And finally, you have to decrypt the file system. Don't worry, we'll go through the steps with something more visual soon. We discovered during the audit some families of keys which were using the CD-ROM partition to store the tools to unlock the key for those who are providing a password-protected USB key. It's used for convenience, at least it's a read-only partition from the operating system point of view. And it also provides you with the auto-run feature, which will prompt you for the password as soon as you plug the USB key. So this is the key, one of the key that was vulnerable to this kind of attack. We already saw that this is not epoxy. Then you remove the chip. You put the chip in an NAND reader to be able to extract the content. And that's basically what you have. So if you look at that, you may think it's properly encrypted. Nothing appears in clear. That's just the effect of the XOR scrambler. So if you look at the data turning the bits into pixels, you start seeing some patterns appearing. You see some scrambled data, and you can see the artifact of the XOR scrambler with the sort of diagonal stripes that appears on those blocks. Then you have some metadata, because they don't change a lot, and that's what will tell you how to reorder the lines on those pixels. Then a bunch of bits that are looking like noise, and that's the ECC correction. And then you go again on the scrambled data and over and over. If you undo the XOR scrambling, that's what the patterns will look like at the end. And if you look at the XDump, it's even clearer that you have undone successfully the XOR scrambler, because you can see some clear text. This is the parameter of the USB stick, which contains some like some strings, some vendor ID for the USB and stuff like that. If you go a bit later, once you've undone properly the file translation layer, you will see the CD-ROM partition. And if you continue a bit down on the memory, you will see the PE file that allows you to enter the password and unlock the key, which means the CD-ROM partition was not encrypted at all. But how do you backdoor that thing? Well, remember the graph, you have to go the other way around, so you patch the exe file so that it can leak the password of the user when you will enter it. Then you have to reapply the XOR scrambler before computing again the error correction code and update it. And then you have to rewrite the memory chip, solder it back, and rewrap the key so that it looks stealthy. Sometimes the manufacturer will help you because no soldering skills needed. It's just a micro SD card on a reader, so you just have to press it and extract the SD card and read it with a card reader. But the thing is, where are the secrets stored? It's an encrypted USB key. Most of the USB key will use AES, and they need this key to be there. It turns out that we had to build a platform to be able to look where the IAS key could be stored, and it was a quite difficult task. So this is the overview of the platform we have. So after desoldering the chip, we connected with individual wires the USB key with an FPGA. The FPGA will emulate the memory and will basically act as a proxy between the researcher's workstation, which contains the data, and we will see the command through. We can tamper with the data and see what happens. And in parallel, we connect also a logic analyzer, which will just analyze what's happening on the wire to ensure that our emulator is working properly. This is a simplified view of the platform. And physically, that looks like that. So here you have the key with the memory chip being removed, connected to custom PCBs that we design, and the FPGA sitting in the middle to emulate the memory chip. And on the top, you have the logic analyzer that will give you the view of the lines. Zooming a bit on the way you have to wire the USB key to the custom PCB. This is again the USB key, the custom PCB, which is a breakout board, and those are individual, very thin wires. And if you look on the USB key, this is what it looks like, and we had to use some duct tape to release the strength, the stress from the wires, because it's soldered on very thin pads, and we broke some keys during the audit. Here you have the view of the logic analyzer, which will give you the digital channels. In gray, in blue, you will have the analog view of the channels, which happens to be very useful because sometimes you have some glitch artifact on the line. that will switch on the digital view a 0 to a 1 and you don't understand why. As an overlay, you can have also your protocol being automatically decoded by the software, and on the right you have the measurement panel. Why were we using the FPGA for that is because the MMC protocol appears to be a high-speed protocol with very strict timings, and emulating it in software was not possible because just the runtime trip between the software emulator and the USB key was going away of the tolerance of the timings. So we had to build it with the FPGA. And this is the output we have on the system. You can see all the commands, the fact that the commands are going from the host to the device, if the CRC is correct, the arguments, and stuff like that. So can the AS key be recovered? Well, that's basically the part that is still work in progress. It's very complicated, and we are looking forward to collaborate on that to get some more resources on that. This is the summary of the storage audit criteria. The most important thing is, as we said, ensure that the data is actually encrypted, and all the data, including the CD-ROM partition. And obviously that some secrets should not be stored in clear in the memory chip. The takeaways from the talk is that the certification is very important, because that's the only way we can audit the cryptographic, the way the cryptography is implemented on the USB key. But on another hand, it's not enough, because it only focuses on the cryptography, and it misses 4 other points that we covered during our methodology. Another point we discovered is that not all the manufacturers, and more important, not all the models from a given manufacturer are equal regarding the security implementation, which means that you cannot trust the reputation of a manufacturer and just look at the package and pick your key. You have to actually audit the key you're going to pick for your company. As the next step, we encourage you to use secured encrypted USB key, because at some point, as we saw on the survey at the beginning, an employee is going to lose a key containing company data on it. We also have to ask for more transparency from the manufacturers so that it's not that hard to audit those USB keys. And because such audit is very time consuming and requires a lot of effort, we believe that crowdsourcing the effort and make it a community effort will be the best for everyone. And I think we have time for a couple of questions, so please use the mic. Thank you.
Please use the mic.
Let's go.